Hello everyone, today we'll talk about the solution to the problem find score of an array after marking all elements. When we look at the situation presented in the problem, we see that we are doing some steps on the whole array and we have to return some value after all the steps are done. And the most natural approach to problems like this is to think about simulating the process. And it's easy to simulate the process in n squared, but we want something better, and that something better will probably be n log n, because we see that this situation here, this fact that we choose the smallest integer at every step, this is very similar to sorting. I don't know if it's possible to implement sorting using a solution to this problem, because that's the standard technique of proving. If you can sort an array using a solution to this problem, then that means that this problem cannot be solved faster than n log n. Of course, we're only looking at comparison sorts. But in this case, yeah, n log n is a lower bound on the time it will take us to solve this problem. And that means that we can use any n log n approach that we like. And the two most natural approaches here for the simulation is either to use a priority queue, to use a heap, because heaps are typically used when you have to simulate an algorithm that always wants the smallest value or the biggest value at every step, and the available values change. But here we can also sort the array, and typically when we have an option to sort the array instead of using a binary search tree or using a heap, it's better to sort, because while all of those are n log n, since sorting is just something that you do once and it's done, and then you just traverse the array, it's typically quite optimized. You don't have to do all those operations that take log n time, and it turns out to be faster. So it's essentially the fastest n log n thing that you can do, sorting. So to simulate using a heap is pretty straightforward. I guess whatever approach we choose, we have to remember this marking the chosen element and its two adjacent elements, but that will be solved, regardless of our solution, by just remembering both the value and the index. We have to remember the index because we have to break ties based on an index. And in that case, we just want to either maintain a separate array of marked that has the same length as our original array, and it's either true or false depending on if the element was already marked, or a set of marked elements. So I'll be having the set of marked elements. When we take an element I, we just update it with I minus 1, I, and I plus 1. So that's very simple. And the simulation using a heap is very straightforward here, and the simulation using sorting is also very easy, because we can just sort the elements in the order of preference, so just looking at the first step. So vi for iv in enumerate nums, this is all our values, the value and the index, and of course we want to sort first by value increasing, then by index increasing, that's this tiebreaker. Of course we sort it, and now we'll be remembering our result, going through the values. We have the value, we have the index. If that index was marked previously, we do nothing, otherwise we add the value to the result, and we mark the three fields. And since we are using a set, we can just blindly put I minus 1, I, and I plus 1. We don't care if we mark the same spot multiple times. We also don't care if this is, for instance, minus 1, or if this is n. If we had an array, a list, then we'd have to probably put an if statement around this factor. And of course, at the end, we return the result. So, as you can see, the approach using a heap will look essentially the same. Just instead of going through all the values, we'll be going through while there are still some values on the heap, but this logic will be the same.